Okay, so we are ready. Thanks to Professor Bush, right, for using his slides. Now, I'll talk about two things today. First, NFA. Normally, NFA means non-deterministic automata. That means when we have non-deterministic choices for each state where to move, right, for a given symbol. Okay, so NFA, and then I'll show you after giving you the couple of examples, motivations, and formal definition of NFA. I will give you an example how to convert NFA to DFA. There is a conversion. So that is very useful. And why we study NFA? Because while solving certain problems, it is easy to design NFA rather than DFA. Okay, so that's why people focus on designing NFA. And if you want DFA from NFA, there is a way you can convert into DFA easily, right? So that conversion is there. Later on, I will show you, as you know that regular languages are languages which are accepted by DFA. Similarly, since DFA and NFA are equivalent in terms of the languages they accept, so basically you can show that every DFA is in NFA. I'll show you how. And then I will, since every NFA can be converted into DFA, that means both are same basically in terms of the languages they accept. That means in terms of computational power, they are same. But NFA are easy to design. We have more flexibility in the design process. So you will see that it is very easy. By the way, last class I posed that question, A and BN. किसी ने solve किया? A and BN? Not possible, why? So basically, there are two main reasons why we cannot do A and BN language, A and BN by DFA, because I need to somehow keep a track of N, how many A's and how many B's, right? Same number of A's, same number of B's. So I have to keep a track of those number N, and I don't have any memory. There is no memory in NFA. So that's why we cannot design something. Or if you really want to design in a different manner, probably you require infinite number of states. That is also not there because we have finite number of states. So in both of these reasons ensures that you cannot design DFA or in fact NFA as well. Later on you will see that for the language A and BN. Okay, I think कुछ लोग आ रहे हैं भाग करके, right? Message गए हैं सब? Fine. So non-deterministic finite automata. So our alphabet is singleton A. And look at this picture. So we have a start state, accepting state. At this start state, after receiving input A, I have two choices. Either I go to state Q3 or I go to state Q1, right? This is the non-deterministic choice for us. So what we should do? Any thinking? Abhi kya kare? On a one symbol A, I have two choices. Either I go to state Q1 or I should go to state Q3. What should I do? Go to Q1. Why? Well, that may not be the case. In this example, that looks okay, but actually, in general, I need is general thought process. And the general thought process is, after starting from here, after receiving A, you go in both the directions. What is the problem? Parallel. Go in parallel. This direction and in this direction. So run in parallel. Both the choices, you run in parallel, right? Then the question becomes, which one we should accept, right? So in parallel, computation is going on, and whenever input is consumed and you reach the final state in any of the computational process, you accept the string. Got it? So that is how you, so once you receive a input A and there are multiple choices for you, you move in parallel, right? So computation will become parallel in all computational paths will run in parallel. And once input is consumed, and in one of the computational path, you reach to the final state, then you accept the string. That is a basic idea about acceptance in NFA. Let me give you a couple of examples. One more thing. So you can see that there are two choices for a one symbol. That is a possibility. Also, there is no transition. Remember, in the DFA, deterministic finite automata, the key property was for each input symbol, A or B, you know where to go. Here, that may not be the case. There is no transition. I don't know where to go if I receive A. Suppose I am in this is state Q2, and if I receive A, I don't know where to go. So that is allowed. In non-deterministic finite automata, it is allowed. No transition is allowed. Okay, fine. And one beautiful thing is left, which you will see. So first choice, AA. You go here, you go here. So one path of computation, all input is consumed, and you reach to the final state. Fine. Second choice, you read A, and input is not consumed, so you reject. So one choice you accept, one choice you reject. So NFA accepts a string if there is a computation of the NFA that accepts the string. That is, all the input strings is processed and the automation is in accepting state in one of the computational path, right? In one of the computational path, then we accept. Got it? This is very important, difference from DFA. So now you see that AA is accepted by this because this is computation accepts AA, and that AA is rejected, right? If you take the other path. So that computation is ignored. Rejection example, single A. It will go Q1, reject, or if you go the other side, then also reject, right? So input is consumed, you are not in a final state, so you reject the string, right? Another rejection example, AAA. You read A, reject because input is not finished. Second possibility, A, you reject, input is not finished and you are in the reject. So AAA is rejected ultimately. Got it? So an NFA rejects a string if there is no computation of the NFA that accepts the string, right? So if there is no computational path among all those parallel computations that those which are going on, right? None of them is going to be in the final state after input is consumed. So then you are going to reject it, right? So for each computation, all the input is consumed and the automation is in non-accepting state, or input cannot be consumed. If that is also the case, the input cannot be consumed, then also it is a rejection case. Very clear? टीवी देख रहे हो क्या? Anyway, so look at this. Singleton A rejected by this NFA, right? On this path, is it rejected? Other part also it is rejected because it is not reaching the final state. Triple A, all possible computation lead to rejection, right? Very clear to you. If the language is AA, so, and the automata is this, you can see that on one side we go to, so this is the actually, why this is a automata that accepts that AA, because on one path of computation, you reach to the final state. Input is consumed, right? Now the most beautiful thing that is there, it is lambda transition. What is lambda transition? Let me show you. Lambda transition is used for providing delay in the computation. Suppose you want to provide a delay in the computation. You don't want to consume the input for a certain period of time, but you want to change the state. Okay, so you provide lambda transition. So for example, you starting from here, you go here, lambda transition, you change the state, then proceed, right? Let me show you. So AA, you read A, you go to Q1. Now there is a delay. You're not reading the input in the next step. You just change the transition. input head, input tape head does not move, but automata changes the state, right? And then you go to A. So you read the another A and go to the accepting state. So string AA is accepted. So now you can clearly see the use of lambda transition. This is allowed in NFA. So remember, what is the difference between DFA and NFA? In NFA, there are multiple choices for a given input. Property number 1. Property number 2, there are no transitions for a given input. That is also a possibility. Property number 3, there is lambda transition. There is a possibility of lambda transition in the system. So these kind of properties allow you, it's kind of a flexible construction. You can handle complex problems easily with this kind of construction, right? That's why it is very useful. Okay. Now, AAA, is it a acceptance or rejection? So you see that A, lambda transition, so you're not reading the input, you move, again A. So input is not consumed, right, completely, and you reach to the accepting state. So this string A is rejected. Any question? Please do ask me questions. If you don't ask me questions, so either you understand everything, you are super genius, or you don't understand anything. There is only binary. Either you don't understand anything or you understand everything. What is the case? Yes. बनाना पड़ेगा. ठीक है, that's good thing. प्रॉपर्टी पे जाना पड़ेगा ना. If there are parallel computations going on, right? हाँ, तो वैसे तो अभी केस मैंने दिखाया है ना. I have shown you that in one path it is rejection, but the other path it is acceptance. So if there is at least one path which accepts it, you accept the string. दोनों साथ में ट्राई करो. बना के देखो, I think. ठीक है. Okay, so the language is AA. So now you can see that this automata has language AA because A is there, then lambda transition and A is there, right? Another NFA example. Now you see, watch it carefully. Starting from AB. So you read A, move to Q1, read B, move to Q2. Now watch it very carefully, something very important. Now there are two lambda transitions, right? So what will happen? It will move to Q3 and Q0, right? I mean, it will move to, basically, you are in accepting state, input is finished, so you accept it, right? You accept it, right? But in the next case, what happens? If it is AB, now AB, you reach up to Q2, input is not finished, you move further, there is a delay. So lambda, A, B, right? So AB is accepted, okay? So now here, AB is finished, then lambda has provided delay in the computation so that you can again come back and start with the next AB part of the string, right? So actually this automata will accept all the strings of the form AB, 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 and so on. So essentially, remember there is a notation when empty string is not there, AB plus, right? All the strings of this form will be accepted by this automata. Another NFA example. This accepts 1 0 star. So lambda. So basically all the strings form from 1 0. 1 0, 1 0, 1 0, 1 0, 1 0, 1 0, and on. So we write it like this. These are the shorthand notations. I will explain later on what does in more details about these expressions, right? So this is the automata for. So for you, यहाँ पे answer तो दिया हुआ है, but from this you try to construct the NFA, right? Or from NFA try to find out the language. These are the two problems which are very, very important. Okay. No, okay. Now look at this. This is a DFA or NFA? NFA. Why? There is no transition is not there, right, from this Q0. And of course, this is accepting empty state, right? Nothing is there, तो कुछ करना ही नहीं है, right? Fine. What about here? There is a lambda empty string. So we need to have a double circle, otherwise we cannot accept this, right? Right? Now you look at NFAs are interesting because we can express languages easier than DFA. Language is singleton A, both the sides, M1, M2. Here is NFA, here is a DFA, you see. Why there are more states? Because for each state, there has to be transition for each input symbol. That is a property, which is making sure that you have this additional state, right? All that additional business. Here it's very simple. A, go and accept. So NFAs are easy to design, right? Very good. Here is a formal definition of non-deterministic finite automata. It's a 5-tuple bunch of states, input alphabet, for example, A comma B. Normally, I think in our course, we are only focusing on A comma B or 0 comma 1, simple forms. I'm not going into too many complicated ones, but I think in the assignment, there are few non-trivial ones which you can do. Delta is a transition function, just like that we have a transition function in DFA, we can define here. Q0 is the initial state. Capital F is a set of accepting states. There are multiple possible accepting states, maybe possible, right? Okay. Now transition function is a set here. In the DFA, delta of Q comma X is equal to P or whatever, or Q prime. Remember, there is only single state. Here, because for one input you can go into multiple states, so actually transition function is a set, right? It will give you a set. Because Q, after receiving X, you can go into following states. That means delta QX is Q1, Q2, QK. Right? So delta of Q01 is Q1, fine. Delta of Q1, 0. After receiving 0, you can go into two states, Q0 and Q2. So that is what it is, right? Delta of Q0, lambda. Lambda transition, you can go to Q2. So it is Q2, fine. Delta of Q2, comma 1. You are in state Q2 and after receiving 1, where to go? No transition. So it is phi, empty, right? Now we can define, just like that, we define delta transition function in DFA and then delta star to operate on the strings. Here also we are going to do the same thing. So delta star Q0 A, for example, here delta star Q0 A is Q1. I'll show you for a couple of examples for strings. So delta star Q0 AA. So Q0 A will give you Q4 and Q0 AA will also give you Q5. So it is Q4, Q5, right? Clear? Delta star Q0 AB. Q0 AB. So A or B will give you Q2, right? But then, because of lambda transition, you also have Q3 and Q0. Okay, so up to this point, you stop. Similarly, for any special case, for any state Q, Q belongs to delta star Q lambda. Fine. And I think you can do this. I'm just skipping this. You can have. So finally, the language of NFA is, the language accepted by NFA is all these strings W1, W2 up to Wn, such that delta star Q0 Wm is bunch of states in which at least one of them is accepting state. Natural choice by the definition, right? One of them should be accepting state. There is some QK which is accepting state. There could be more, which is okay. Now let us again look at this example. Delta star Q0 AA. Q0 AA will give you Q4, Q5, right? So AA belongs to this language, right? This is the example. F is the accepting state is Q0, Q5. There are only two accepting states, Q0, Q5. What about delta star Q0 AB? AB. So A will give you this and B will give you Q2. But then there is a lambda transition, so you will have Q3 and Q0 as well. Right? and Q naught is accepting state, so AB belongs to language, right? One of them has to be accepting state, right? Delta star Q naught AB AA. A, B, then there is a transition, lambda transition, you come here, A and A. You can go into Q4 and you can go into Q5 both, right? So it is Q4, Q5, right? So A belongs to language. Oh, I think something wrong. Yeah, whatever it is, you can correct it. I hope that's good. Yeah. तो डिले प्रोवाइड करने के लिए ना हाँ यहाँ पे see what I'm saying that here actually we want to see that what are the possible states you can reach. So you know from here we can always reach, because there is a lambda transition, we can reach up to Q3 and Q naught anyway. So there is an error in the, we need to write Professor Bush, there is a problem in the slides. I have not made it anyway. So, anyway, so now you look at ABA, right? So ABA, A, B, and then lambda transition will come back here, and then A. So Q1 is the only possibility, right? So Q1 is a non-accepting state. So this string ABA is rejected, right? Does not belong to the language, correct? So overall language is this anyway. Okay, so one portion, the background of NFA now you know. To show you that NFA can be converted into DFA. That is the main target. How to convert an NFA to DFA. Okay, that is a beautiful thing. So let us look at this beauty. We have. So how will you show that two languages are equivalent? I mean, two automatas are equivalent. One machine is equivalent to the other machine if they accept the same kind of languages. So if language of M1 is same thing as language of M2, then we say that M1 is equivalent to M2. Okay. We are going to use this fact to show that DFA and NFA are equivalent. DFA is one machine, NFA is one machine. And DFA and NFA are equivalent if you can show that the language accepted by DFA is same thing language accepted by NFA, and language accepted by NFA is same thing as language accepted by DFA. Right? So one portion is straightforward, clear, because every DFA is in NFA. Why? Because NFA seems to be more general, right? DFA is a special case, right? So every DFA is NFA. So every language accepted by DFA will be accepted by language accepted by NFA, right? So we need to show the reverse side. This is what it is written, you know. See, all this theorem form में लिखा हुआ है, but actually जो कह रहे हैं वो common sense है, right? So we need to show that languages accepted by NFA contains regular languages, and language accepted by NFA is a subset of regular languages. Regular languages I have defined languages which are accepted by DFA. So the first thing, every DFA is trivially an NFA. So any language L accepted by DFA is also accepted by NFA. So regular languages are a subset of languages accepted by NFA, right? Clearly, this will happen. This portion is a little bit non-trivial, but I can show you. Languages accepted by NFA is subset of regular languages. That means any NFA, I will show you that any NFA can be converted to an equivalent DFA. And if you are able to show this, then we are done. Rather than showing you the complete proof, I will give you an example so that you capture the essence, right? With that example, later on in the slide, proof is given which you can look at it, right? While drinking a cup of tea, you can look at the proof, right? That is okay. Okay, so let us see how to convert NFA to DFA. NFA is this Q0, Q1, Q2. Three states are there. One accepting the state Q1. Sigma is A comma B, right? And there is of course lambda transition. So this is an NFA, non-deterministic finite automata. So what we do, we look at the start state Q0, and I'll make a state here in DFA, singleton Q0, and a circle. And this is our first starting point. Okay, starting point. I am making a DFA, right? Now what I do, I look at Q naught here. From Q naught, where I can reach. After you, if you receive A, what you will get? Q1. So since alphabet is A comma B, I need to provide transitions for both A as well as B, right? I should provide, right? In this state, if I receive A, where to go? If I receive B, where to go? I need to provide it. That I can check. If I receive A, I am reaching to Q1, right? So I am just making this. So Q naught, after receiving A, we go to Q1, and also because of lambda transition, Q2 is also there, right? So Q1, Q2 is our next state. After receiving A, this is the first state, this is the second state. New state that I have created from this, right? Now, is it complete? No, because I need to tell what will happen if I receive B. So B is missing, right? So what we should do? ठीक है, एक B लगा दो, एक फालतू की स्टेट लगा दो नीचे. Phi, some phi, trapped state phi. If I receive B, you go here. If you receive A, we go here. Still, it is not complete, but half of it, right? Okay. Now what we do? Now from this Q1, Q2, also I should tell you if I receive A, where to go. If I receive B, where to go. Now this Q1, Q2, if I receive A, that means I should tell you what will happen if I receive A on Q1 and if I receive A on Q2 in this NFA, right? So that we can see that once we receive A at Q1, when we receive A, what we are getting? Q1 itself, right? And also because of lambda transition, Q2. So on Q1, after receiving A, I am getting Q1, Q2. And what about the second Q2, right? I need to tell about Q2 also. If you on Q2, if you receive A, what will happen? Q2, if I receive A, there is phi. No transition, right? So that is second thing. So the first thing, delta square Q1 A, delta star Q1 A is Q1 Q2, and delta star Q2 A is phi. And so the combined state, take the union, is this Q1 Q2. So that means I need to make a transition A from this to this itself. Got it? Not very difficult, just common sense, right? From the looking at the NFA, we are just designing how to. Okay, now what? Is it complete? Now I should tell you what happens if I receive B, right? So again, we can check the state on Q1. If I receive B, I am getting Q naught. On Q1, if I receive B, right? So lambda transition is there, that will give you Q naught, right? So Q naught is there, and similarly on the state Q2, what happens? Q2 on receive, again you are getting Q naught, right? So in both the cases, from here, if I receive B, I am getting Q naught. So I can make. So basically union is Q naught. So I have made a transition from here to here, this B. This portion I have made, right? Got it? Now what else? Is it complete? Any idea? Is it complete? What is missing? Phi. I need to tell what happens if I receive A and B. And what is the best choice? Loop, dal do, khatam. So you are learning how to do this business, right? You are done. So from NFA, I have converted into DFA. Right. I have shown you an example. General theory works in a similar manner. Just take a cup of tea and enjoy. Yes. हाँ वो भी बनानी है यार. फाइनल स्टेट क्या है? इसमें Q1 है फाइनल स्टेट, तो Q1 इसका सबसेट है, तो इसको फाइनल स्टेट बना दो. राइट. हाँ ये सर्किल डाल दिया ना मैंने. Q1 is a part of it, right? तो इसको बना दिया. So now basically जो वहां पे था ना, so now this DFA is complete now. From NFA, this DFA, it has a start state, it has accepting state, and for every state, for every input symbol A or B, I know where to go. This is the very important property, which is a property of DFA. It holds here now, right? Got it? Rest of the all this equivalent, general conversion, blah blah blah, all this you can read. खाली कुछ है नहीं उसमें एक्चुअली. ओके, सो वो पार्ट 1 इज ओवर. अभी कितना टाइम बाकी है? हाँ, 3:20 हुआ है ना. एक मैं तो क्विज के लिए सोच रहा हूँ एक्चुअली ना. और अभी आए थे 2:50. अभी तो बहुत टाइम है, कोई दिक्कत नहीं है. ओके, so now the next topic is all about properties of regular languages. You just saw that EFA gives you regular language, NFA gives you regular language, right? A language is said to be regular if there exists a DFA which accept it, right? That's the definition of regular language. Now I'm going to show you properties of regular languages, and I can obtain different properties of regular languages using the business of NFA. NFA is a very easy for us to actually play with. Okay. So, by the way, this picture you should remember for entire of your life, right? Because this is the summary of computer science. You are doing BTech in computer science. This is a summary. There are 4 machines: finite state automata, push down automata, linear bounded automata, Turing machine. There are only 4 kind of machines possible. Each accepts certain kind of languages and each have certain kind of grammars. So right now I told you about finite state, both DFA and NFA, right? Later on I will talk about push down automata, but before that I'm going to talk about regular languages. I already, by definition what is regular languages. I'm going to show you the properties of regular languages, right? And then we'll come to the push down automata. LBA normally I don't do in this class, but we can talk about Turing machine later on. So this is a summary. And this was done by Noam Chomsky, who is a linguistic professor, right, in 1956. By the way, there is another beautiful thing. Each of these languages can be specified by its production rules, right? So each of these production rules, like using certain grammar, right, which produces the languages. When these production rules act in parallel, in most of these things, these are sequential. यहाँ से यहाँ गए, फिर sequence पे दूसरी जगह, फिर दूसरा rule लगाया. Actually, but when you apply them in parallel, you get any idea what you get? Beauty is there, wow. You actually get beauty. All these trees that you see, forest, trees, flowers, they all follow that thing, what is known as L system. There's a whole branch known as algorithmic botany. So you see, this is the difference between common man and the people who are very rich. This guy, Steve Jobs, you might be knowing, right? He used these concepts to form Pixar, the company, for animation, for creating animation using these principles, and these rules apply in parallel, actually, So you can create flowers. So like that, if you observe, there's a lot of symmetry in the tree, right? You go 2 steps, and then at right side, 50-degree angle, there is a branch. Then again, there is a branch at 50-degree angle with certain path, right? Everything is very nicely done. There is a book you can search, Algorithmic Botany. Okay, Algorithmic Botany you can search. Similarly, there is a book. So you see, people who are leaders, they know this is like Steve Jobs knew about it. Actually, created a company for creating these animations. In animations, you create forests, trees, and everything using these algorithms, right? And these production rules are applied in parallel. That is very, very important. Just I mentioned. There is also another book, Algorithmic Seashells. Seashells, So those seashells, the algorithms for actually observing pattern on the seashell is also because of these computer science principles, right? There is a beauty anyway. Good. Now, properties of regular languages. Again, thanks to Professor Bush for using the slides, because I have to say every time. So I have taken permission from him. Okay, so for regular languages L1 and L2, we will prove that union is regular In concatenation of is regular, star is regular, reversal is regular, complement is regular, and intersection is regular. Okay. So I will show you a couple of initial things up till the complement using the business of NFA, non-deterministic finite automata. So basically what I will do, L1 is, for L1 there will be NFA, for L2 there will be NFA, and I will show you how to combine them to get the, regular language L1 union L2. I will show you NFA for the union. Okay. Similarly, I will show you NFA for the concatenation. I will show you NFA for the L1 star and reversal and complement. Okay. So observe, it's not very difficult, but conceptual level, in 5 minutes you will learn this concept. So that means we say that regular languages are closed under these operations. If something is regular, the union is regular, concatenation is regular, star is regular, reversal is regular, complement is regular, and intersection is regular. So now actually you see that here in NFA we have two accepting states. What I can do, I can modify, I can always make two accepting state into single accepting state by putting these lambda transitions, right? This is very useful trick. Okay, and now you will see that while combining, we will use these kind of tricks. Actually, this is very useful thing, right? From two accepting state, you make equivalent NFA with one accepting state. Okay, so here it is. In general, we have NFA, bunch of accepting state, start state. I am not worrying about what is in between, right? There is something is going on. I don't care. I'm looking at only the initial state and bunch of the final states, right? In the NFA. So equivalent NFA is, this is a trick. Just take a single accepting state and add lambda transitions for each of them, right? That is a trick. So NFA without accepting a state, if this NFA is without accepting state, I can use accepting a state without transition. That is also a possibility in NFA, right? Extreme case. Anyway, so take two languages, L1 and L2. Both are regular languages. Since both are regular languages, there exists NFA for them. So NFA machine M1, take a start state, accepting state, start state, accepting state for M2. Single accepting state, single accepting state. Now I am going to combine them. This is just an example, okay, for L1 and L2. Union. So for the union, what you do, M1 is there, M2 is there, a start state, and put lambda transition to the start state of M1 and start state of M2. Okay, and that's all. This is the union. Accepting states could be any number of them. I don't care here actually, so that works. Here is an example for it, which we can verify. Concatenation, what we do? Take this accepting state, take it as a general state, and put a lambda transition to the start state of the other one. Okay. So now will have this start state and this final state. The combination. This is the concatenation. Okay. L1, L2. Similarly, so this is an example which you can see. I'm just skipping all that. The star operation, what you do? Take the NFA, put a start state, accepting state, combine everything by lambda transitions from here to there, lambda here to here, and lambda there to, and then you delete this accepting state and make this as a new accepting state. This is for the star operation. Okay. This lambda is very beautiful thing, right? You do whatever you want. This is the example for lambda. Reverse. So this is the NFA. Reverse it. Make this as accepting state, the other one as a start state. This is the reverse business. So reverse all transitions, make initial state accepting state and vice versa. And you are done for reversal. Here is an example. Complement. This is L1. Complement, you do actually this. This is your accepting state and becoming actually, the start state will become accepting state, and then, to take the DFA that accepts L1, make accepting state non-final and vice versa. Okay, then you are done with complement. Once you are done with these many things, then intersection is easy to prove. L1 is regular, L2 is regular. We need to show that L1 intersection L2 is regular. So what we do? We apply this De Morgan's law. L1 intersection L2 is equal to L1 complement union L2 complement. If L1 is regular and L2 is regular, their complement will be regular. You just saw that. Their union will be regular. You just saw that. Complement of that union will be regular. You just saw that, which is nothing but intersection. You are done. Intersection is regular, right? बाकी सब बकवास है. All done. So basically, we have covered DFA, we have covered NFA. अभी कितना टाइम है क्विज के लिए? अरे जरा काउंट करके बताओ कितने लोग हैं? 140 हुए? प्लस है. ऐसे मैंने सोचा था पुश डाउन ऑटोमेटा शुरू करूंगा, ठीक है, इट्स ओके. ज्यादा ज्यादा पढ़ना ठीक नहीं है. तो बट जब पढ़ना है तब पढ़ना है, राइट? या तो सुबह 4 बजे पढ़ो अपना जो है ना चोटी बांध करके सुबह सुबह, और या फिर आजकल सुबह तो लोग उठते नहीं है, भूल गए, राइट? रात को 2 बजे तक चैटिंग. Anyway, so I think that's all for today. See you in the. By the way, just remember I may take a quiz. अभी मेरा मूड बन गया है. Anytime there may be quiz, so that you are studying it regularly. Regular study. If you do regular study again and again, I am stressing you. You make group among them, among yourself. 2-3 people. Evening चाय पे बैठो and जो भी problems हैं उनको resolve कर लो, खत्म. In every subject. पता भी नहीं लगेगा सेमेस्टर ओवर हो गया.